Ladies and gentlemen, good evening. I'm sure most of you know who I am, but just in case, Danny Nobis, Pro-Vice Chancellor for External Relations. As always, gives me great pleasure to welcome you all to tonight's public lecture. I would like to extend a special welcome to the Deputy Mayor and Mayoress of Hillingdon, Councillors George and Judith Cooper. This is sadly the last public lecture of the 2014-15 series, but I can promise you that next year, which will also be our 50th anniversary year, we will be back with another series, and we're actually not going to have a public lecture, but a series of public debates. The details will be announced very soon via the website, so please keep an eye on that. Once again, the lecture will be recorded, edited, and made available via the website. Someone actually mentioned to me that some of the previous year's recordings have attracted a great many views. One of them, I think it's the one about what is reality, has attracted something like 15,000 views, which is quite staggering, I think. You can also contribute to the debate by posting a message on our Facebook page. That's facebook.com/Brunel University, or via Twitter using the address @BrunelUni and the hashtag Brunel Lectures 2015. Finally, by way of housekeeping, I'd like to remind you to turn your mobile devices to silent mode so that they don't interfere with the discussions. Once again, we don't have any fire alarms planned, so in the unlikely event that the fire alarm does go off, please make your way to the nearest exit and some stewards will be at hand to take you to an assembly point. Now, the topic of tonight's lecture is the science of good health, and we are delighted to welcome to Brunel Dame Mary Archer to share with us her views on this subject. I wasn't entirely sure what Dame Mary was going to talk about under this heading, so I thought that by way of introduction, I would present you with some basic facts and figures, if only because that's what scientists tend to rely on. Facts and figures. I'm a social scientist and not of the quantitative sort, so all of this is still a little bit strange to me, but there you go. Some basic facts and figures about good health. At the beginning of the 20th century, the average world life expectancy, according to my source of information, which is the United Nations World Populations Prospects, was approximately 30 years. Yet in 1985, it had risen to 62 years. According to the same source, for 2012, the average world life expectancy stands at 71 years, whereas the UK average is 81. In the UK, life expectancy at birth increased by almost a decade in the first 50 years of the NHS, which, as I'm sure you all know, was established in 1948. In 1948, 40% of people died before reaching pensionable age, but by 1996, it was reduced to just 7%. Currently, Japan has the world's highest life expectancy, 86.2. Followed by Andorra. I don't want to be patronizing, but just in case you don't know where that is, it's a tiny little country between France and Spain, which has a very high life expectancy for reasons that are not entirely clear to me. 84.2. In third place is Singapore, 84. It's generally believed that this extraordinary increase in the world's life expectancy during the 20th century is due to tremendous improvements in public health care, enhanced nutrition, but also to spectacular advances in medicine. And I think Dame Mary tonight will tell you a little bit about how medical developments over the past 10, 20, 50 years have contributed to life expectancy and indeed to good health in general. To give just one example, because of vaccinations and antibiotics, childhood deaths have been significantly reduced in recent years. As I was looking at these figures, as a social scientist, I thought, well, this is extremely interesting and great. We've made tremendous progress, but some challenges do remain. And I'm not sure we will be able to address these, but I nonetheless wanted to highlight them to you as a non-expert in the field. And I thought of at least 5 issues that probably will need to be addressed as a result of this progress, or apart from, or maybe despite the progress. One, there seems to be a clear correlation between life expectancy and national and individual wealth. Whereas Japan tops the list of countries with, as I said, an average life expectancy of 86.2, the average life expectancy in Sierra Leone is almost 50 years less and currently stands at 38. With the exception of Haiti and Afghanistan, all of the world's 40 countries with the lowest life expectancy are in Africa. 2, a higher life expectancy is not by definition synonymous with a better quality of life. At the risk of being unnecessarily controversial, I'm tempted to say that maybe there is now also more suffering amongst the human population, although Mary may disagree with me, than before, because many more people live longer in sickness and disease, and with physical and emotional pain that cannot always be effectively alleviated. 3, increased life expectancy and good health, combined with declining or stable birth rates, leads to population growth and to an aging population, which brings about new socio-economic and political challenges pertaining to, well, one, the volume of available workers, but also the organization of health and social care, and, as we all know, to a revision, a necessary revision of pension commitments. 4, insofar as life expectancy and good health are crucially dependent on new advances in diagnostic technologies, new surgical procedures, and again, I'm sure that Mary will enlighten us about that, and new state-of-the-art pharmaceutical treatments, the availability and implementation of these life-saving and or life-enhancing developments seems to be conditioned also by economic and value for money factors, so that good health may still be embedded within a utilitarian calculus. And 5, many of the most advanced medical technologies, such as stem cell therapy and genetic profiling, they raise important ethical questions. Ethical questions about how far we, as human beings, can and should go in order to rebuild and regenerate ourselves. I think that these ethical concerns are likely to become even more prominent in the next 50 years or so, when thanks to 3D printing technology, we may very well be in a position to print entire body parts. Hence, whereas we probably have every reason to be cheerful about how scientific developments during the 20th century have vastly improved the health and well-being of the global human population, we may also need to put our optimism about the 20th century's medical progress into a bit of perspective, or at least remain aware of how scientific progress may have a downside to it, or maybe more than one downside. So here to enlighten us with her views on the science of good health is Dame Mary Archer, our eminent guest speaker for tonight. Tough, resolute, and inquisitive from an early age, Dame Mary conducted her first empirical study at the tender age of 10, when she tied an earthworm into a knot to see if it could untie itself. Apparently it couldn't. Commenting on the experiment, she said, I quote, "It's a good job I wasn't a trained scientist, or I'd have knotted at least 100 earthworms to make the results statistically significant," unquote. Inspired by her chemistry teacher at Cheltenham Ladies' College, Dame Mary read chemistry at St. Anne's College, Oxford, and physical chemistry at Imperial College London. And she taught chemistry at both Oxford and Cambridge universities. From 1988 until 2000, she was the chairwoman of the National Energy Foundation, and she now serves as the foundation's president. Between 2002 and 2012, Dame Mary was chair of Cambridge University Hospital's NHS Foundation Trust and a founder director of Cambridge University Health Partners. Dame Mary is also the chair of Imperial College Health Partners Expert Advisory Board, of the UK Solar Energy Society, and of the Guild of Church Musicians. Earlier this year, I hope I got this correct, she was appointed chair of the Science Museum Group, where she reportedly, quote, "feels like a child let loose in Hamleys without adult supervision," unquote. She's a trustee of the UK Stem Cell Foundation of the Britten Symphonia, and she has recently joined the Hydrodec Group plc as a non-executive director. She was appointed Dame Commander of the Order of the British Empire in the 2012 birthday honours for services to the NHS. Ladies and gentlemen, please welcome Dame Mary Archer. Thank you.
Well, thank you, Danny, for that very kind introduction and for giving part of my lecture so beautifully. Few of us are born with perfect health. We inherit, if not the sins of our fathers, at least the genetic idiosyncrasies of our parents. Even if we've been dealt a good genetic hand, throughout our lives we'll be exposed to injury, infection, and disease, so that many of us, at one or more times in our life, will have relied on the wonders of modern medicine to restore us to good health. Until comparatively recent times, medicine was an art rather than a science, a collection of beliefs, knowledge, and experience practiced by surgeons and physicians with very little in their medical bags to enable them to relieve the suffering of their patients. But the techniques and therapies used in modern medicine are squarely founded on science. And it's about how that underpinning science has developed and what it's now making possible that I'm going to talk this evening. I'm particularly pleased to be doing so here at Brunel because the university is a distinguished member of Imperial College Health Partners, which is a collaboration between the 3 universities and 18 NHS organisations in the 8 London boroughs shown here of northwest London, all working together, as our strapline says, to drive innovation through collaboration. Peter Beresford, who's Professor of Social Policy here at Brunel, has recently joined the Partnership's Expert Advisory Board, which I chair. But there's a second reason I'm pleased to be speaking at Brunel, the university. Brunel the man is better known for his bridges and his railways than for hospital design, but he was a pioneer in this area too. When Britain entered the Crimean War in 1854, some old Turkish army barracks at Scutari became the British Army Hospital. Florence Nightingale and 38 of the nurses she'd trained were sent out to staff the hospital, where Florence, the lady with the lamp as she became known, found absolutely appalling conditions. Medicines were in short supply, hygiene was neglected, and fatal infections were common. She wrote to the Times asking for help, and the government responded by commissioning Brunel to design a prefabricated hospital that could be built in England and shipped to the Dardanelles. In just 6 days, rivaling God's timetable for the creation of the world, Brunel designed a 1,000-bed hospital of 60 modular timber wards. The design was revolutionary. Each ward had siphoning water closets, ventilation, drainage, and even rudimentary temperature control. By Christmas 1855, Brunel's hospital had been shipped to the Dardanelles and assembled at a place called Renkiol. The death rate at the new Renkiol Hospital was less than 1/10 of that at Scutari. And thus a hospital design that would endure for over 100 years was created by the driving vision of Florence Nightingale and the genius of Isambard Kingdom Brunel. Florence Nightingale is rightly regarded as the mother of modern nursing. Here I pick out 3 of the founding fathers of modern medicine: each memorialized in a fine statue. On the left is Edward Jenner, the father of modern immunology, depicted in this statue in Genoa, inoculating his 11-month-old son in 1797 with his experimental vaccine against smallpox, one of the deadliest and most feared diseases of the time. His vaccine was pus, from the pustules of a patient suffering from the milder disease of cowpox. Jenner was excoriated, particularly by the Church, which does not have a good record of embracing new medical technology, for using the effluvium of disease in this way. But it worked, and vaccination against smallpox was made compulsory in Britain in 1853. Oops. In the middle is Louis Pasteur, the father of modern microbiology, whose statue there sits in the Court of Honor of the Sorbonne. It was Pasteur, 3 of whose 5 children died of typhoid in childhood, who discovered that wine or milk soured only if germs got into them, germs, invisible baddies that got into such things and soured them. And of course, it was then that the technique of pasteurization, heating such things to kill the microorganisms, was devised. This discovery led Pasteur to the germ theory of disease, the idea that disease is caused, as indeed much of it is, if microorganisms invade our body. On the right is Joseph Lister, rather elaborate statue. The lady with her arm upraised is humanity, saluting Joseph Lister. This statue is in Portland Place, near his former home in Park Crescent. Lister heard about Pasteur's germ theory of disease and reckoned that carbolic acid, which was then used to reduce the awful stench of sewage, might be doing so by killing these invisible germs that Pasteur thought existed in the sewage. So he started to use it to spray his operating theatre and clean the wounds of his patients. In 2 years, the death rate of Lister's patients from post-operative infection fell from 46% to 15%. It was on Lister's advice on what we'd now call aseptic surgical technique that saw the future King Edward VII safely through a very risky operation for appendicitis 2 days before his scheduled coronation. Lister got his reward when the king recovered and made him one of 12 original members of the Order of Merit when the coronation honors finally happened in 1902. Modern surgery would not be possible without anesthesia and highly skilled anaesthetists to keep patients safely in that narrow space, narrow corridor between consciousness and death during an operation. Before the use of ether and then chloroform as anesthetics, patients had the option of whiskey, opium, hypnotism, or biting on a leather strap to see them through the agony of surgery, which had to be carried out at great speed. London surgeon Robert Liston, described by his admiring colleagues as the fastest knife in the West End, could amputate a leg in 2.5 minutes in the 1830s, though on one occasion he took off the unfortunate patient's testicles at the same time with the flourish of his knife. This painting shows the famous first use of ether as an anesthetic by surgeon William Morton, there excising a tumor from the unconscious patient's neck. Here's the chap holding the ether bottle. He's a dentist. That was in Massachusetts General Hospital on the 16th of October, 1846, and they've kept that old lecture theatre, which they now call the Ether Dome, exactly as it was in those days. Robert Liston, the chap who'd had the accident with the testicles, heard about this use of ether and adopted it as soon as he heard about it, performing the first operation in Europe using ether and as an anaesthetic at University College Hospital, another member of the Imperial College group, and commented afterwards, the patient having been, of course, insensible, "This Yankee Dodge sure beats mesmerism hollow." How do we get from this to this? From the mid-19th century to the beginning of the 21st century. Modern surgery, here using a robot surgeon, or a surgical robot, I should say. Well, by a whole range of advances, all of them based on science. And I'll pick out some of them this evening, starting with diagnostics, finding out what's wrong with the patient. Nothing's had greater impact on the development of various imaging methods that allow doctors to see inside the body without opening it up than X-rays. X-rays were discovered by Wilhelm Röntgen in 1895, for which he won the first Nobel Prize in Physics in 1901. On the left, you see the X-ray image Röntgen took of his wife Anna's hand, complete with her wedding ring. Anna was disconcerted, perhaps understandably, at seeing her own skeleton thus revealed. "I have seen my death," she commented. But in fact, images such as these have saved countless lives by showing up injuries or abnormalities in the body which can be accurately located and treated. How are these life-saving X-ray images made? Well, X-rays are generated by firing electrons, these little black dots, in a vacuum tube across which there's a big potential difference across these two electrodes. Here's an anode, usually made of tungsten. When the electrons strike that, they emit X-rays, the red arrow there. The patient is not actually levitated, but lying on a table normally. The X-rays pass through the part of the body to be imaged. Some of them are absorbed, and some of them come through. And they fall onto a detector, which in the early days was a fluorescent screen, a screen of a material that fluoresces when X-rays fall on it, just on card or glass. And in a modern X-ray machine, it's normally a scintillator, a rare earth ceramic, which puts its little needles of light into a huge array of photodiodes beneath, very much like, if you like, your computer screen is divided up into pixels. Now, X-rays are penetrating. They travel through air, like visible light, with very little attenuation, but they're strongly absorbed by dense substances, more strongly so by heavy atoms than by light ones. Bones are strong absorbers of X-rays because they contain the relatively heavy elements calcium and phosphorus, while the soft tissues of our bodies, which are largely made of the light elements hydrogen, oxygen, carbon, and nitrogen, absorb X-rays more weakly. Hence, X-rays are very good at showing up broken bones, but if the radiologist wants to take an X-ray image of your intestines, you may have to swallow a barium meal, or if he wants, or she, wants to look at your blood vessels, you may have to have an injection of an iodine containing contrast agent. Barium and iodine both being very heavy elements and very good absorbers of X-rays. X-rays were quickly pressed into action in World War I. Here you see a surgeon looking for bullets embedded in a soldier, an early example of image-guided surgery. The X-ray generator is, here's the vacuum tube under the table, passing upward through the patient. Here's the detector. These rather awkward-looking goggles are simply a mask to keep out light, and then a fluorescent screen enabling the doctor to visualize the insides of the patient and receive goodness knows what dose of radiation as he does it. This technique, fluoroscopy, so called because the X-rays are rendered visible by making a substance fluoresce, is still used in the modern C-arm fluoroscope, which is a familiar sight in cath labs, for example, helping the radiologist to guide that catheter up from the groin up into the heart. X-rays took a great leap forward thanks to the work of this chap, Godfrey Hounsfield, an electrical engineer who worked at EMI labs. He worked out a method for taking a whole set of X-ray measurements all around the patient, then using computers, relatively primitive in those days, to build up a much more detailed X-ray picture, thus inventing the technique that's called CT, computed tomography, tomos meaning a slice, I think, if you know your Greek, which I most certainly do not. EMI was the company that recorded the Beatles, and it's often said that Godfrey Hounsfield was allowed to mess around with this daft idea until it worked, exactly because they lived so well off the royalties of the Beatles' early hits. In the CT machine, the X-ray source and detector are in the donut, as it were, and they're rotated around the body at high speed, taking X-ray measurements from all angles and moving slowly along the body. Well, actually, the body moves slowly into the donut to build up images slice by slice until the radiologist's got what he wants. And stunning images can be made. Compare this old-fashioned 2D plain film chest X-ray. There's the X-ray machine, here's your chest, there's the photographic plate or the fluorescent screen at your back, and that's what you get. Still used to see if there's a mass that shouldn't be there in the lungs. But contrast that with this, a 3D image of a shoulder built up by CT. The color is false, but the rest is absolutely real. And you can see the exquisite detail in which the surgeon or the physician can examine, as it were, the patient to find out what's wrong. Here's another remarkable CT image. It's a colon, and this is a virtual colonoscopy done by subtracting everything that isn't colon out of the picture. This is a nice, healthy colon, no polyps or tumors, but that would, of course, be picked up by this technique, though it's not routinely used, A, because it does expose people to a small dose of ionizing radiation, and B, because if you do see a polyp or a tumor, then you've still got to do the old-fashioned kind of colonoscopy to get it out. This is a different kind of imaging machine, an MRI scanner, a magnetic resonance imaging scanner. It looks a bit like a CT scanner on steroids. It's bigger and fatter, but it works in a different way. Unlike CT, MRI doesn't involve the use of ionizing radiation, as X-rays are sometimes called. So it's preferred for use on children and babies, as X-rays are particularly dangerous if you have them at the start of what one hopes will be a long life. Also, it takes a lot longer to do an MRI scan than a CT one, and MR machines are rather noisy. I don't know if you've ever been in one, but they do make a rather irritating sound. And that goes on for quite a bit of time, perhaps 10 minutes to do a scan. However, you can get stunning and different sort of images out of an MRI scanner, because it's much better than CT at looking at those soft tissues that we have, the ones that are made of the light elements that don't really absorb X-rays. So compare and contrast these two images of the lumbar spine, that's the bit in the small of your back. The one on the right is 3D CT, very nice but very bony, and the one on the left is an MRI image showing the bony bits, but also showing these things, which are the discs, which are not made of bone. They're made of a kind of spongy, cushiony material, and they are, of course, the spine's shock absorbers. Down here, this patient has a herniated disc at L4, L5. That's the bottom of the lumbar spine, which tends to be the bit that goes wrong because it bears all the weight of your torso and upper body in the last bit of the spine that isn't fused so that things can move. MRI can also detect the subtle difference between the grey and white matter in the brain, as you can see on the left. So it's good at picking up tumors in the brain, which you really couldn't see with CT. Not that it would be a good idea to direct too much X-rays in through the brain anyway. I've made the point that X-rays are quite dangerous. You don't want to have scans for fun, as it were, though the doses are now very small. But of course, in larger doses, X-rays are used in radiotherapy to kill tumors, and they have to be carefully targeted on the tumor, not to harm too much normal tissue around the tumor. But in addition to showing up the structures in the brain, MRI can actually show us what we're thinking, or at least whether we're thinking, and that's the picture on the right, fMRI, or functional MRI. Here the scanner is detecting the oxygen levels in the blood vessels of the brain, using the difference in magnetic properties of oxygenated and deoxygenated hemoglobin. When we concentrate on a particular task, that part of our brain demands more oxygen. So there's a local increase in blood flow to regions of increased neural activity. And in fMRI, those parts of the brain are visualized as red, whereas less active parts are shown blue. So this patient is thinking hard at the back of his head, if you see what I mean. fMRI is very useful for examining things such as brain function after a stroke, or for assessing patients in a coma to see if and how their brain responds to any stimuli. How does MRI work? Well, I've borrowed a set of cartoons from the web to show this. The patient lies on a table, round which is coiled a very powerful superconducting electromagnet. It goes all round the patient, but I've just shown it on either side. And that's a superconducting magnet cooled by liquid helium. So the current goes on in it forever, and the magnetic field is very stable. And here's the lines of the magnetic field, and there's the patient lying in it. A typical MRI machine has a magnet, has a strength of 1.5 Tesla, which is about 30,000 times stronger than the Earth's magnetic field, which is why you have to be very careful not to have any metal objects in the MR room, or indeed in the patient. Some people with certain kinds of metal implants cannot have MRI scans. Now, our bodies are largely made of water. I think the average person has 43 litres of water if it were all boiled off. Wouldn't leave much behind, really. And water is, of course, H2O. And hydrogen atoms have an interesting property which is called spin. They don't really spin, but physicists give these things daft names, charms, quarks, and things. Anyway, so spin gives each hydrogen atom a tiny magnetic moment of its own. And when the patient lies in the machine, the hydrogen atoms line up in either the low quantum spin state, low energy, or fewer of them in the high energy state, just according to Boltzmann's laws, those of you who are interested in such things. The burst of radio waves that makes that irritating noise is then switched on from some kind of radio coil, and it passes through the patient, and that has just the right frequency. It has to be chosen to have the right frequency, the so-called resonant frequency, to excite some of the low energy hydrogen atoms into a high energy state. The radio frequency burst is then turned off, and the extra ones that were excited up here relax back to the ground state, emitting their own burst of radio waves. And it's those radio waves that are picked up as a signal and turned by some very, very clever underpinning mathematics and very fast number crunching by computers into an image of where those hydrogen atoms are. Now, the exact frequency of the emitted radio waves depends on the chemical environment of those hydrogen atoms. So, for example, water in a tumor is typically chemically slightly different in its environment from water in normal tissue. So tumors show up in MRI as different from normal tissue. And to get sharp images, MRI images, slice by slice, in fact, I said the magnetic field is constant. I told a bit of a lie. It has to be focused and defocused slice by slice so that you just get an image of one slice at a time rather than a whole lot of overlapping sort of blobs. And it's that rapid change of the magnetic field that sets the coil twanging like a kind of discordant guitar string and makes that irritating noise. NMR is getting ever more sophisticated. This rather delightful movie clip of twins seemingly fighting in the womb appeared on YouTube quite recently.
It's a womb with a view, a unique view of a twin pregnancy. The images were made possible by a recently developed Cine MRI scan used by clinicians at London's Centre for Fetal Care. Dr. Marisa Taylor-Clark says the technology offers new perspectives on dual pregnancy.
Didn't know sibling rivalry started quite so young. It's interesting, there are one twin's much larger than the other, and that will need attention. Typically what they do is they, with a laser, redivide the placenta so more blood goes to the undernourished twin. A different method of imaging, one that's widely used, actually again for babies in the womb, is ultrasound. This is a safe, noiseless, and relatively inexpensive method of imaging. Again, it doesn't use any ionizing radiation, which is why it's the method of choice for scanning expectant mothers. This is my second grandson, Harry, at 20 weeks gestation in the womb. And there he is, bless him, at 20 weeks in the world. Making an ultrasound image is based on the same principles that bats use when they find their way, and by fishermen when they seek to locate a shoal of fish. They send out sound waves, and when sound waves strike an object, some of them are reflected back. That's how you hear echoes, particularly if you yodel in a resonant place like the mountains. The echoes that come back can be used to give you information about the object that has reflected that sound. Now, ultrasound is very, very high frequency sound. We can't hear it. Even bats won't hear medical ultrasound, though their ears do go up, as it were, much higher in pitch than ours. Ultrasound won't pass through air, which is why they put that nasty cold gel on the end of the probe before they put it on your nice warm body. Ultrasound also won't pass through much fat, which is why it's never really caught on in the States. How's ultrasound made? Well, by using an effect called the piezoelectric effect. This is shown by certain classes of crystals, and it's a property that makes the crystal expand or contract slightly if an electric field is placed across it. So it might expand for plus minus and then contract for minus plus. So if you apply a rapidly changing high-frequency AC current, the crystal is set into vibration, and it is vibrations, of course, that cause sound by knocking the air molecules, and off the sound goes through the air. So piezoelectric crystals can generate ultrasound. The best materials are so-called PZTs, short for lead zirconate titanate, whose structure you can see here. The red balls are the lead ions. The big blue ones are the oxygen anions. They're big. And the little thing in the middle, there's only one of them, there's not 4 or 5 of them, is zirconium or titanium. And that's the one, it's sort of loose in its cavity, and that's the one that vibrates. It's positively charged, so it's attracted to the negative end of an applied field. And that's what causes the whole dimension of the crystal to vibrate along that axis. And ultrasound is detected simply by the reverse of this effect. The ultrasound that's reflected by the object that's being imaged falls onto a piezoelectric crystal, making it vibrate. It's attached to a couple of electrodes, and you see an AC electric signal flow that's then analyzed to build up the ultrasound image. Another physical effect, the Doppler effect, is also used in ultrasound imaging. It's the Doppler effect you hear as an ambulance with its siren blaring whizzes past you. As it approaches you, the sound waves that its siren is emitting are bunched up in the air by the relative motion of you and the ambulance, or the ambulance and you. The frequency is raised, and higher frequency corresponds to higher pitch. As anyone who's ever tried to tune to concert A at 440 with a Baroque instrument tuned at 415 will know very well. As the ambulance goes the other way, so the sound waves are kind of spread out and the pitch falls. It's exactly the same with ultrasound. The frequency changes if the ultrasound is reflected off a moving object. And the useful thing to look at here is blood. And the red cells in blood reflect ultrasound nicely. So you can use ultrasound to look at the direction of blood flow, for example, in a varicose vein or a leaky heart valve. Doppler ultrasound is also good at seeing cancerous tumors because they create their own blood supply as they grow in a process called angiogenesis. This is the inside of my bladder on the 30th of October 2010. On the left, in plain ultrasound, with a large mass that shouldn't be there and a couple of smaller lumps that shouldn't be there either. And on the right, in Doppler ultrasound, showing a large, well-vascularized grade 3 tumor. A sobering sight, I can tell you, at the time. But that's all history now, as I have a very fine new bladder made out of 1/2 meter of my small intestine plumbed in. I'll turn now from imaging to another cornerstone in the development of modern medicine: advances in therapeutic drugs. Using herbs to treat disease goes back thousands of years and continues today in traditional Chinese medicine. This slide shows the magnificent Materia medica cabinet of one Giovanni Francisco Vigani, the first professor of chemistry in the University of Cambridge. Colleges seldom chuck things out, and this cabinet has stayed where it was in Queen's College since Vigani taught there medical students in the 1690s. You can see 4 drawers from his cabinet on the right. They hold not only many plant extracts, but also mineral pigments. For example, the red mineral is cinnabar, which contains the toxic element mercury. That was ground up into an ointment and applied to the sores of people suffering from the dreaded disease of syphilis, then a much more virulent disease than it is now. That was by no means a certain cure. Indeed, many of Vigani's cures were of the kill-or-cure variety. And mercury causes appalling side effects. Even in the 19th century, there were very few effective drugs, leading the American physician and author Oliver Wendell Holmes to remark, "If all the medicines in the world were thrown into the sea, it would be all the better for mankind and all the worse for the fishes." It was not until 1909 that the German physician and scientist Paul Ehrlich synthesized the first drug that specifically and successfully targeted a specific pathogen, the spirochete bacterium that causes syphilis, still at that time one of the most lethal and infectious diseases in Europe. The compound he made was dubbed salvarsan, and the ARS bit for arsenic. You can see a little triad of arsenic atoms there in the middle of that small molecule. It was Ehrlich who coined the term chemotherapy for the action of drugs such as this, though nowadays we would reserve that term for the drugs that are used to treat cancer. Salvarsan was dubbed the magic bullet drug because it acted specifically against that one type of bacterium that caused syphilis and did very little in the way of side effects. We'd now call it a narrow-spectrum antibiotic. It was Alexander Fleming's discovery in 1928 of the drug that came to be known as penicillin that heralded the dawn of the broad-spectrum antibiotic, something that is effective against a wide range of infections. Here is Fleming in his laboratory at St. Mary's Hospital in Paddington, another of the hospitals in the ICHP group, incidentally. It's said Fleming made his great discovery because there were 2 kinds of window in St. Mary's Hospital, those that wouldn't open and those that wouldn't close. And he left his petri dishes growing colonies of staph bacteria next to one of the latter kind, went away on holiday, and when he came back, he was astonished to see all of them covered with colonies of staph, except one where there was no staph, but there was a mold growing in the middle. I can't help feeling that many people, myself included, would have looked at that and thought, well, that's no good, and chucked it out. But Fleming did not. As he commented, one sometimes finds what one does not expect to see, and that mold, from that mold, was extracted the material penicillin. It's another small molecule drug, as most antibiotics are. You can see its structure on the right. And thanks to the work of Howard Florey and Ernst Chain in Oxford, penicillin was turned from a laboratory curiosity that had to be extracted from the juice of the mold into something that could be synthesized in the lab and was made available for widespread use in World War II for the troops. Penicillin remains a widely used antibiotic today, so widely used indeed that many strains of bacteria have become resistant to it because they can moderate their behavior according to what one throws at them. And antibiotic resistance, as you'll know, poses a great threat to the future control of infections and infectious disease. So don't take them unless you really need them. The 3D structure of the penicillin molecule, and it's important to know 3D structures, how the atoms are related in space, because that will very much determine what they lock onto and don't lock onto in the body. And sometimes mirror image molecules are quite biologically different in their activity. Anyway, so the 3D structure of penicillin was established by the great chemist and Nobel laureate Dorothy Hodgkin, who worked to develop the then fearsomely laborious technique of X-ray crystallography, no computers then, to deduce the structure of biological molecules from maps such as these shown on the walls of the little chamber that houses her model of penicillin. Dorothy was a very senior and distinguished member of Somerville College when I was a very junior and undistinguished member. And I was thrilled to discover when I became chairman of the Science Museum this January that it is we who hold that famous model of penicillin, which she made in 1945. She went on to establish the structure of more complicated molecules, notably vitamin B12 and insulin. And then computers took over, and if you can crystallize your molecule, which is often half the battle, then your computer will analyze the structure. The next class of life-saving drugs, which emerged on the scene in the late 80s, 90s, are monoclonal antibodies. Now, antibodies are naturally occurring protein molecules. We all have thousands of them and make thousands of them, thousands of different types of them in our bodies as part of our natural defense system against invading baddies, antigens as they're called, such as bacteria or viruses, Pasteur's germs, that can get into us and cause infection and disease. When our bodies detect an antigen, here's the antigen colored yellow, then either our immune system summons up an antibody. If we've been challenged by an antigen before, this antigen, we will have a memory in our immune system, and that will make the right antibody. If we haven't been challenged with it before, we'll probably be a bit iller as a result of the antigen invading before our immune system comes to its senses and makes the antibody for us. And they work because the antibody is made with a cavity, typically, of exactly the right molecular size and shape to lock on to the antigen. A lock and key analogy is entirely apt here. One lock, one key, very specific. And that locking on flags the antigen for destruction by phages in the immune system. Antibodies were discovered, I mean, not as such, but their action was discovered more than 100 years ago. It was known that if you injected horses or sheep with, for example, small amounts of tetanus or diphtheria toxin or snake venom, the serum that you could withdraw from the horse's blood would have some magic curative property, which is actually the antibodies that the horse has made to that toxin, which you can then use, and that's still used as an emergency treatment for snake bites today. But it's not really suitable for large-scale use. You don't want to keep large numbers of horse and sheep to infect them with things and then get the toxin out. And B, if you do, you'll get a whole range of things out. And C, the human body doesn't like animal stuff put in it, and you will sooner or later get a reaction. So that was an interesting discovery that needed further development, and it got it through the brilliant work of César Milstein and his postdoc, Georges Köhler, working at the Laboratory of Molecular Biology in Cambridge in the mid-70s. They discovered how to clone antibodies, so make large numbers of identical antibodies in bacteria. And that was a step forward because now you could make a controllable antibody, but they still derived from animals, typically from rats or mice, and they still weren't very suitable for human use. And that's where Greg Winter and Herman Waldman, also in Cambridge, came in. Between them, they developed what's called a humanized antibody, monoclonal antibody. Humanized meaning all the sort of animal bits had been taken out and replaced by human type material. They again could be cultured and cloned in large numbers, and thus we got monoclonal antibodies, for which Greg and Herman won the Nobel Prize in Medicine in 1984. It was Greg who administered the first humanized monoclonal antibody to the first patient. He's now Sir Gregory Winter, Master of Trinity College and very grand, but he was then a postdoc at the LMB down the road from Addenbrooke's Hospital, where there was a patient desperately ill with advanced non-Hodgkin's lymphoma. I think ethics committees weren't really getting going in those days like they do now, but anyway, Greg asked the lady if she would be prepared to take a course of this experimental antibody. They called it Campath 1H, 1H for the first humanized one, Campath for the Cambridge Department of Pathology. And the lady said, yes, I want to live until my daughter is married. And so she had a 30-day course of injections of Campath 1H with the remarkable result you see here. One of the features of advanced Hodgkin's is this enormously enlarged spleen, which has retreated to virtually normal size in 30 days. She did live to see her daughter married. Today, 6 out of the 10 best-selling drugs in the world are monoclonal antibodies. Humira for the treatment of rheumatoid arthritis, Lucentis, wet macular degeneration, and Herceptin for the treatment of HER2-positive breast cancer are 3 examples. The next great advance in drug therapy, genomic medicine, has been a long time coming. In fact, it's only really starting to happen now. But it began on the 28th of February 1953, when Francis Crick and James Watson burst into the Eagle pub in Cambridge to announce to the startled regulars that they had discovered the secret of life. What they'd discovered by building these very simple molecules out of bits of Meccano and clamps was the now famous double helix structure of DNA, deoxyribonucleic acid, which is a very long molecule. It would be 1 meter long if you stretched it out end to end, that's found in the nucleus of all our so-called germline cells, most of the cells in our body, in fact. The 2 strands of the double helix are held together by hydrogen-bonded base pairs. And adenine always bonds to thymine, so green bonds with, what do I call that color? Lavender. And pink, cytosine, always bonds with guanine. So you see each sort of rung of the double helix is held together either by an AT or a CG pair, and that's what they had discovered. During cell division in our bodies, the DNA unwinds into 2 single strands, and a new strand is built on each as each base in that strand binds in its complementary base. So if there's an A here, it'll attract a T and bind that onto the new growing strand. If there's a C, it will bind in a G. And thus it is that 2 faithful copies of DNA are made every time a cell divides. At our conception, we receive 1 strand of DNA from our mother and 1 from our father, and they combine to make our own unique DNA. Our DNA carries our genes, which are particular lengths of the genome, as it's now called, typically some tens of thousands of letters long. This 4-letter alphabet goes down the chain in a particular order that varies only slightly from one of us to another. And the secret of life, as Crick and Watson had it, is held in that 4-letter alphabet, because our genes determine all our characteristics. And if there's one or more spelling mistake in a gene, our health may be adversely affected. Now, spelling mistakes, mutations, may be inherited from our parents, or they may arise over the course of our lives if our DNA is damaged by radiation or by exposure to certain chemicals, or occasionally by a simple copying error. It's good, but it's not perfect. Some diseases, such as Huntington's disease and cystic fibrosis, are caused by a mistake in the spelling of a single gene, a so-called single gene defect. The first disease to be characterized as a single gene defect was sickle cell anemia. Normal red blood cells are like little sort of squashed balls that travel along your veins and arteries quite happily. But in sickle cell anemia, some red blood cells, or some of them, have this elongated sickle shape, and they tend to clog up the arteries, particularly at joins, which is dangerous and also can be acutely painful, apart from giving the patient severe anemia, which gives the disease its name. Here's the spelling mistake that causes that disease. So in a normal gene, there's a little 3-letter sequence that's called a codon because it's coding for something. That is GAG, guanine, adenine, guanine. In the sickle cell mutation, that A has become a T because what is AT in the normal gene has become TA, swapped around. Still fits, but it's wrong. And that codes via messenger RNA for the wrong protein. These little codons code for making proteins. And this code makes what it should, GLU, glutamic acid, and that is a normal protein in the hemoglobin. And this mutated codon codes for a different amino acid, valine, which turns into a mutant protein that causes the hemoglobin to clump together. So, as I say, that's an example of a disease that's caused by a single gene defect. Those are the kind of mistakes that are typically arise when 2 carriers have children. So by a carrier, we mean an individual who's got 1 normal copy of the gene and 1 abnormal one. Normally the normal one is dominant, otherwise we'd be a massive mistakes, and the mutated one is recessive. So if 2 carriers have children, just simply by Mendelian thinking, they have a 1 in 4 chance of having an unaffected child, having inherited the normal strands from both parents, a 2 in 4 chance of having a carrier child who will be healthy but will carry the disease, and a 1 in 4 chance of having a child who has the disease because they've drawn the short straw and inherited the mutant gene from both father and mother. And that's how these distressing diseases like Ivan Cameron, David and Samantha Cameron's son, Ivan, who had Ohtahara syndrome, that's a disease caused by this kind of recessive behavior. Here's another striking example of a single gene defect. It's a rare type of obesity that's caused by a single gene defect, which means that the body can't make the hormone leptin. Now, leptin is the hormone that we make as we're eating, and it tells us when we're full, more or less, and so we stop eating. But people who can't make leptin don't have that sense of fullness or satiety. They're always hungry. So, of course, they tend to overeat, and they become very obese, as this unfortunate child on the left is. That was detected by Steve O'Reilly and his group in the Institute of Metabolic Science in Cambridge, and a daily course of leptin restores normality to that child, as you can see on the right. Not many diseases, well, let me turn that round. Most diseases are caused or are influenced by more than one genetic characteristic. And a number of diseases, particularly cancer, are caused by mistakes in a whole number of genes, not just one. And this is much harder to sort out because our genomes contain about 3.2 billion base pairs of A, T, and CG. And about 22,000 genes. And that's a lot of sorting out. Simply reading all those 3.2 billion letters of the whole human genome was an enormous international endeavor. You may remember the Human Genome Project, which ran for 10 years. There you see President Bill Clinton with Tony Blair joining by video link, announcing that the human genome had been sequenced in the year 2000. Well, it more or less had, actually. At that time, there were still 150,000 gaps in the genome, and since then, I think there have been about 38 reference genomes filling in those gaps published. But it was a huge step forward and a huge endeavor. It took 200 scientists, 10 years, and about $3 billion to complete the Human Genome Project. Since then, the sequencing machines, fascinating technology, but I won't go into it, that read DNA letter by chemical letter have got much faster and much cheaper. And the cost of reading a genome has plummeted, as you can see. It's now down to about $1,000 per genome and set to fall further with a new generation of sequencers coming onto the market. That means that personalized medicine, or precision medicine as it's called in the States, is becoming a reality. This means giving patients with a particular disease therapy that is targeted at the mutations in their genome that is causing that disease, rather than a one-size-fits-all drug that has passed some kind of double-blind clinical trial. This slide shows the example of breast cancer. It's a map made of the genomes, the genomic characteristics of breast cancer tumor cells from 2,000 women. And you can see it sort of looks a bit like a demented tartan. There are in fact 10 clusters that are genetically like each other but different from the other clusters. And the interesting thing is that those clusters are associated with different survival Some are more aggressive than others. This yellow one, cluster 5, is not a good one to have, whereas this brown one, cluster 3, is much more indolent. And that's very important information for the oncologist. It reduces the chance, which I'm afraid is very common in breast cancer, of over-treating simply because you don't know whether you're dealing with a pussycat or a tiger tumor. Gene maps like this have now been made for some lung, bowel, and blood cancers, and we are discovering that cancer is not one disease, it is hundreds, if not thousands of degrees, genetically speaking. And in many cases, we have some drugs that are available or can be repurposed to hit some of those now identified genetic mutations. And in other cases, we now know what we've got to hit, and so drug discovery is going a different way, and clinical trials are going a different way too. So I think it's a time of great promise. But there's much more to do, particularly for cancer and for children with those rare inherited diseases that we were looking at just now. And that's why a large number, well, a considerable number of national projects to read people's genomes are now underway, and why you may be a member of Biobank, for example, the UK Biobank. You've been asked to deposit a sample of your genetic material by spitting into a tube and sending it off to a lab, to bank your genetic information to be used for the purposes of research. Back in 2012, David Cameron launched the UK's 100,000 genome project, which will sequence the genomes of 40,000 NHS patients, different number of genomes and patients, because if it's a child, then you sequence both parents, and if it's a cancer, you sequence the tumor and the normal tissue of the patient. And that information will give us an enormous amount of information, particularly helping doctors to diagnose rare diseases. The typical patient with a rare disease, it will take 7 years to diagnose it correctly, by which time, of course, it may be very advanced when it could have been treated more successfully early. Not to be outdone, in his State of the Union address this January, President Obama announced the US's Precision Medicine Initiative to sequence the genomes of no fewer than 1 million Americans. And sooner or later, and certainly within a generation, I would say, having your genome sequenced will be a routine part of medical care. Another new branch of medicine that's showing great promise is regenerative medicine, a subdivision of which is stem cell medicine, as Danny alluded to. This involves replacing, engineering, or regenerating human cells, tissues, or even whole organs to restore or establish normal function. In 1999, the world's first engineered organ was transplanted into the chap on the left, Luke Masella. He was born with spina bifida, which can cause very poor bladder function and cause urine to reflux back into the kidneys, which damages the kidneys severely, which is, of course, life-threatening. So the American surgeon Anthony Atala, shown on the right there, who'd been experimenting with tissue culture for years, grew Luke a new bladder. He made a bladder-shaped bag out of a natural biopolymer. I'm not sure if it was collagen, but something like that. Took some cells from Luke's natural bladder, not cancerous, that's important. This wouldn't work for a cancerous bladder, too dangerous, and seeded the scaffold with them. And cells do what cells do. They divided and replicated and made a new bladder, which Dr. Atala transplanted into Luke, and 15 years later, he's coexisting very happily with his engineered bladder. Here's another very striking example, and I hope it can be replicated, of using healthy cells to replace damaged or missing ones. Now, you'll know if you cut your finger, the nerves in it will regrow. You won't have a numb finger forever. But if you sever the nerves in your spinal cord, they won't regrow and you'll be paralyzed. The more so, the higher up in your spine you break your spinal cord. In 1985, Professor Jeff Raisman, on the top left there, working at UCL, discovered that we have specialized nerve cells called olfactory ensheathing cells at the top of our spinal cords, just at the base of our brains. These are cells that, nerve cells that give us a sense of smell, and they do grow back if they're damaged. Raisman reasoned that maybe they were near enough to the spine that they could be used to repair damaged spinal nerves. And he spent many years experimenting on animal models before in 2010, a chap in the lower left, Darek Vedika, a Pole, a rather argumentative Pole because he'd been paralyzed in a knife fight that had gone wrong 3 years before, became the first human patient to have his olfactory ensheathing nerve cells, OECs, taken out in a little operation, cultured in the lab, and put into the lesion in his spine. He was paralyzed from the chest down, and 3 years later, it's not perfect, but he can walk with a frame, and he can use an exercise bicycle. And there is MRI evidence of spinal nerve regeneration. So I think that really would be a miracle of modern medicine to make the lame to go. Another organ that's full of nerve cells is the eye, very complicated organ. And many common eye conditions that can lead to blindness, such as glaucoma and age-related macular degeneration, are caused by the loss of nerve cells in the retina, a very, very complicated, multi-layered structure in which cells are laid down, these are the rod and the cone cells, with exquisite precision. Not an easy structure to make in the laboratory, but in Cambridge, many of my examples are from Cambridge because that's where I picked up most of this rather unsystematic information. In Cambridge, Professor Keith Martin, who's head of the Department of Ophthalmology, with his colleague Barbara Lorber, are adapting 3D printing, which we're all now quite familiar with, a modified inkjet printer, which is now printing live retinal cells, a cell at a time, on a little biopolymer to make a synthetic retina. Not going into a patient yet, but I'm sure it's only a matter of time. And one of the nice things about these cells is they know where they ought to be, and if you don't put them down quite right, they migrate to where they ought to be. After all, that's what they do in the natural organism. Well, I started my talk this evening with Brunel the man and his revolutionary hospital design. Let me finish with Brunel the university and another kind of revolution that we need in medicine, telemedicine, to keep us safely at home and out of hospital if we don't need to be there. The idea of telemedicine is that diagnosis and monitoring of health conditions is done by moving data about the patient rather than the patient, him or herself, to the clinician. Maybe by a handheld or a wrist-held sensor, such as the ones you see here. Could be an Apple Watch. Dr. Malcolm Clark, who's reader in telemedicine and e-health systems here at Brunel, is an expert in telemedicine, and he's worked with Dr. Russell Jones at Chorleywood Health Centre, a few miles up the M25, on 2 projects to show how health data collected by such an unobtrusive device, worn by the patient, can be sent to the health centre via a home wireless gateway, such as most of us have, the Zigbee technology, for example, in your smart electricity meter that sends your meter reading to your billing company. And in future, it's essential, I think, to cope with an aging population that more sophisticated and widely used telemedicine is adopted. So congratulations to Brunel at the forefront of modern trends in healthcare, just as Brunel, the great engineer, was in his time. I thank you for your attention this evening, and I shall be happy to try to answer any questions you have, but I should remind you that I'm not a medical doctor. As was borne in on me many years ago when I just got my PhD and I went to work over one long vacation at Brookhaven National Laboratory in the States. The amiable porter who helped me take my luggage up to the girls' dorm looked at the new luggage labels, proudly inscribed Dr. Mary Archer. He sighed and he said, "You real doctor, missy, or you kind of doctor never did no good to nobody." I had to admit I was the latter kind of doctor, so I shall approach your questions with a proper sense of anxiety. Thank you.
We've got a good half hour for questions, and I'm sure many of you are dying to ask Dame Archer a question, so I won't ask you any questions myself, really. I just want to say that I think you were too kind to the fMRI, or the MRI, when you described its noise as irritating.
Yes, maddening.
I was in one a couple of months ago. I'll spare the details, but the noise was unbearable. And the radiographer knew it, because he gave me, I called it an anxiety pair. You know, it's a little rubber thing.
A worry bead, as it were.
Yeah, something like that you can press if you're about to have a panic attack in the scanner. And he also gave me headphones, and he said, if the noise is really too bad, I'll play some music. And after 5 minutes, the whole procedure, right, it's about 45 minutes, by the way. After 5 minutes, I couldn't stand it anymore, so I said, please play some music. And he played AC/DC. Heavy metal. You probably thought, block out the sound of the magnetic coils with some heavy metal music. So I thought it was unbearable, but there you go. Thank you so much for this wonderful whirlwind tour of recent advances in medicine that have clearly contributed to our good health, but have made massive progress in terms of both the diagnosis and the treatment of various disorders. I'm tempted to ask you more about your vision of the future, and to talk a bit about the challenges that I identified, but maybe people in the audience will want to pick that up. We've got some roving microphones. So who wants to ask the first question? Please keep your questions short, because then we can get in quite a few. Who wants to ask a question? What's that? Got a question here at the front. Sue.
Hello, I'm Sue Jobling, Director of the Institute for Environment and Healthy Societies here. I really enjoyed your lecture. I thought it was absolutely fascinating. But of course, being the Director of the Institute for Environment and Healthy Societies, I'm going to ask what you think the future of good health might be. I mean, you've outlined some of those things in your talk, but do you think the environment will play a role in the future of good health?
Undoubtedly, yes, and of course, historically, it has. If you don't have clean water, then cholera and typhoid and all kinds of waterborne diseases are going to be endemic in your population. Climate change also poses certain kinds of challenge, not only heat stroke on extremely hot days, but the migration of microorganisms that typically didn't get this far north, say. Air pollution, there's no question, but that's strongly related to asthma and respiratory conditions. So yes, a healthy environment is tremendously important. And I think one area, we know we ought to take it seriously, but I think the science of it is still a bit in the dark ages, is nutrition. We are what we eat. And we all know we're supposed to eat 5 a day and all the rest of it, but hell, you know, the donuts are nicer. It's now possible, actually, to look at people's nutritional status, as you'll know, by really looking at metabolites, their metabolome. And I think I read a paper that said 90% of us are malnourished, in fact. One common thing is vitamin D deficiency. There are 6 genetic variations that mean your ability to make vitamin D is impaired. And if you've got all 6, you're in real trouble. But even if you've got 2 or 3, you'll be vitamin D deficient. So, yes, genetics are at the root of many diseases, but by no means all of them. Some, like respiratory conditions, are purely environmental, though they may end up damaging the genome. What's your view?
Well, maybe I should let somebody else ask a question, but you know, I was just thinking more about the recent advances in epigenetics.
Yes, I didn't touch on epigenetics, which is an interesting thing, that you can inherit things that aren't in your genes, but are sort of next to your genes in terms of function, and that's called epigenetics. And that's, yes, that is very much environmentally influenced, isn't it? So we will certainly learn a lot more about this, and some of us will act on that knowledge, but I wouldn't be too optimistic about it, because we all know perfectly well that smoking is very bad for us, and yet a considerable proportion of us still do it.
I'll take a question on this side of the auditorium. The gentleman here in the 4th row. 3rd row? 4th row. Yeah. just raise your hand, sir, and the microphone will come.
I would like to ask you about progress or lack of it in tackling degenerative diseases of aging. I was at a British Science Conference a few years ago where an enthusiastic speaker said the first babies are going to live to 150 or already been born. Many of us said, well, that might be nice, but what's really important is enabling all of us to live to 90 or 100 without suffering from things like dementia or arthritis or some other crippling disease that destroys the quality of life. So what can you tell us about progress in this area?
Well, this is where my not being a medical doctor is going to tell, and it may be that you or somebody else in the audience can contribute more than I can say. Dementia is, again, probably many diseases. There was a paper quite recently that pointed to an inflammatory origin of some dementias, quite different from the protein misfolding paradigm of Alzheimer's. My guess would be that well, we now know a fair amount about the molecular mechanism of protein misfolding and plaque formation in the brain. My guess would be they will find an effective therapy for that, which will alleviate much suffering. And dementia is a much higher priority now. It's been prioritized for investment by the NIHR, the National Institute of Health Research, in a way it never used to be, and there are biomedical research units in dementia. But of course, aging is, it's a process of natural degeneration. The telomeres at the end of your genes shorten, copying errors multiply. And so senescence is, in a certain sense, inevitable. We can stave it off by healthy living and exercise. That's very important. and keeping mentally alert. But I think we have to work for the goal that you perhaps sketch out, that we all drop dead of something very sudden, like a brain hemorrhage at the age of 90. That would be good.
What about the cost of some of these new medicines, whether it's the MRI machines, pharmaceuticals, etc.? How soon can we see them decrease in cost? That's one of the main barriers.
Well, the big machines are expensive, and it's not in the manufacturer's interest to bring the price down. The Illumina sequencers that are used at the present time to sequence DNA are intrinsically very expensive. It's very complex technology. Interestingly enough, there's a company called Oxford Nanopore that's got a $1,000 sequencer based on a nanopore with a stripping enzyme that the DNA slots through quite fast and reads out in real time with an amperometric signal. So there are disruptive technologies that are cheaper, but on the whole, the cost of healthcare is in the people, not the gear. Of course, it's good if you've got expensive assets like MRI machines or sequencers to sweat them. But 70% of hospital costs are people costs. And you can make the technology as cheap as you like, but people and skilled interpretation don't come cheap. So I think that the high-tech end of healthcare is always going to be quite expensive, and we in this country have the NHS, into which we all contribute, like a massive insurance scheme, and it costs, what is it, 110 billion pounds a year? People say it's free, it's not, it's very expensive. Though it is a cost-effective system if you look at some others. But going back actually to something Danny said, improvements in public health, keeping people weller, less ill, is really the only way to reduce healthcare costs. And competition too. It's wonderful how the cost of a machine comes down if you tell them that the other firm has given you 10% off.
Is that a matter of education more than anything else?
What, public health improvement? I don't know. We don't very much like being told what to do, do we?
Precisely.
Yes.
Well, and even if people do tell us what we should do and don't do, that doesn't necessarily mean that we follow the advice, right?
No, indeed.
I'm not
even
going to
if
put
we
my Freudian
do,
hat on and
yes,
say that we are our own worst enemies and that there's a death drive in us. But yeah, I mean, we all know that being aware of the risks of smoking, for example, will not necessarily...
No. And we also know that if you go in for a smoking cessation program, you may relapse afterwards. But
Precisely.
Still, you have to keep trying. I think there will always be a distribution, as there is in every walk of life, as between the keep fit fanatics and the couch potatoes. That's human nature. It's just trying to shift that bell curve a bit to the fitness end.
But my question as far as the cost is, for example, the UK has a great shortage of physicians, so I have more physicians being trained and nurses as well. Also a matter of scaling, as far as if you make more MRI machines or whatever is cheaper for each one you make, or simple things with medicine as well. So it's more a matter of scaling and teaching more people, getting more people trained. Why isn't there a lot more funds going into that?
Well, there is a quota system in terms of the numbers of medical students that medical schools can take. They're always oversubscribed by, 15 to 20-fold, with very, very bright want-to-be students too. And there's a quota system there because it's very expensive to train a doctor, indeed. It's certainly fair to say that the NHS relies quite heavily on foreign-born doctors, and some of them are absolutely superb and bring in great new ways of thinking, and some of them I think are a problem, particularly if they can't communicate well in English with their patients. And nursing, again, relies heavily on foreign nurses. At Addenbrooke's Hospital, we have about 450 Filipino nurses, for example, out of 3,000. So other countries actually are in worse state. I've done some work in Botswana with the health system there, and 90% of the doctors are foreign-born because they don't have, or they didn't have until very recently, their own medical school. It is a problem, and workforce planning in the NHS is no better than it is anywhere else, and it tends to be feast or famine. I would say that there are shortages in certain specialties, care of the elderly, geriatric medicine, pediatrics, also a very demanding specialty with no private work worth speaking of. And we're short of midwives perennially. As the birth rate goes up, we don't train the midwives to keep pace. What's the solution? Paying some of the fat cats in the NHS less and making the system more efficient, I would say, is a good start. Sorry, you were saying something, sir.
I just applied the solution is train more physicians. Is it really fair for another country in East Europe or somewhere else to use our national resources to train physicians and then they go somewhere else? Well, that country loses out on the resources. You just said they cost a lot to train.
They do, though of course the medical students may have to pay their way through medical school, and some, like the Philippines, actually do, as it were, train clinicians for export. That's how they get a lot of foreign currency sent back into the country. I don't have a solution, and I'm not defending the status quo. I think it would be difficult to get it perfectly right. It takes 15 years to train a surgeon. And in that time, the need may change. We don't need any heart surgeons anymore, basically, because statins are so good. I mean, that's a bit of an exaggeration.
I'll take another question. Vice Chancellor. Please, Vice Chancellor.
As you said, genomic medicine opens an enormous potential for treating people in the future, but it also opens the door to multitudes of new drugs. But getting a new drug to market is an incredibly expensive business, and all too often we see things failing at the very last moment, and drug companies, of course, losing a lot of money through that. So are we, with genomic barriers, genomic medicine, going to reach a barrier where we simply can't afford to develop new drugs to treat the diseases we would like to treat?
I don't think so, Vice Chancellor, because the very expensive method is the laborious phase 1, phase 2, phase 3, phase 4 methodology of clinical trials that was really put in place after the thalidomide business, when people realized you had to put safety first. So phase 1 is first in man, healthy volunteers. Phase 2 is a small number of healthy subjects. Phase 3 is the real thing, patients with carefully controlled conditions. Phase 4, large multi-center trials. And the upshot is drug X is better than the previous best drug, drug Y, by 5%. NICE will or will not pay for it in this country according to what the cost per quality is. Well, that is very expensive and very inefficient, but I think genomic medicine shortcuts all that, because if you can see in the patient's genome what is likely to be wrong, you would design an entirely different type of clinical trial for your new drug. You see this mutation or this set of mutations. So you look for a drug which may be there on the shelf, having been licensed for something else that you can repurpose, that you think is going to hit those mutations. And the last thing you do is a double-blinded randomized trial, which is a perfect way to drown out the signal in the noise. Because you're looking for a drug that is effective in, say, 5 or 10% of the population with that disease. So actually, I disagree with you. I think clinical trials will, what I think it will mean will be the death of big pharma. They won't be agile enough. The little companies with the smart ideas are going to have a great time.
Yes, I think we have time for a couple more questions. I'll take your question first, and then I'll come to you, Chris, at the front here.
I know a company that is very...
Could you speak into the microphone, sir?
In nutraceuticals and natural remedies, and on the basis of prevention rather than cure, that a program of self-help is a large component in tackling the huge problems of expenditure and general lack of resources within the medical support organisations. Do you have a view on that, Dame Mary, as to whether that has a role to play in your wonderful scientific discovery arena that you...
Yes, I do. As I was saying to this lady in a slightly different context, I believe, without knowing a lot about it, that nutrition is an undeveloped science. And there's been, as there always is, at the early stage of, as it were, building knowledge, some quackery around it, some, faddy diets and so forth, that have made most people sort of throw up their hands and say, well, if you can't tell me if red wine is good for me or bad for me, I'm going to drink it anyway. So, yes, I think that there is, there's impeccable evidence that some nutraceuticals are absolutely vital. Folic acid in pregnancy, for example, to prevent spina bifida, like that poor chap Luke Masella was born with. But I don't know, and perhaps you can help me, whether I'm right in my surmise that we will get further with the science of nutrition when we know more about our metabolome, how we metabolize food. I was very struck when I learnt some years ago that in the brain of patients with bipolar disorder, their brain metabolism is abnormal. They make malic acid or rather than lactic acid or the other way around. Well, that's absolute clear signal that there is something genetically wrong there.
We're very strong on omega-3
yes.
remedies and the regular taking of omega-3.
Unsaturated fats.
Absolutely.
Yes,
and
oils.
For brain connectivity, effectively. And there's a science that goes back 5,000 years in this.
There's been knowledge that goes back 5,000 years.
Well, the science and current activity and research and certainly products and patents that we hold are clear evidence that this is working. And there's a huge business model there that we're following. But it requires much more constructive input from the individual, rather than wait for something to be found to be wrong. They should be taking
Keep
steps.
it prophylactically.
And I suspect along this road, we're doing that we're taking all sorts of things which may not be a waste of time, but which are there's good evidence to show that they have a beneficial effect. I mean that's the end of my pitch here. It's a terribly important part of it, and I laughed everything else you told us about the developments and so on. We also do serious science within the company, and particularly in new antibiotics and and really anti-inflammatories.
So do you use genetic information at all
We
in
do.
your work now?
We have molecular diagnostic businesses with the group. So we're a combination, really, but we're leading with nutraceuticals
Yes.
as really a wide open field commercially and of huge value to human well-being.
Well, jolly good luck, is all I can say.
Chris, you have the last word. Well, no, I'll have the last word. But you-
As always, as always. Firstly, thank
My
you
show.
for a fascinating lecture. I really enjoyed it. You touched on, as Danny did, I think it was his fifth comment, on stem cell technology.
Yes.
Where do you think that will lead? I know there are some very big political sides to it, but also where do you think it can lead in terms of scientific development?
Well, as you all know, stem cells had a bit of a rocky ride because the early source of them was fetal material, discarded unwanted embryos from IVF, but many people found that quite hard to stomach. Then it was discovered by Hanakawa in Japan that you could turn somatic cells, adult skin cells or whatever, back into sort of stem cells called pluripotent. And the thing about stem cells is that when they divide, they make one more stem cell, but they make a differentiated cell too. So they might, according to where they are, they might make a nerve cell or a muscle cell or a fat cell. So that's stem cells grow into the differentiated tissues of our body. And the idea is that you could take stem cells, if you can find pure strains, and there's a stem cell bank, and repair damaged organs and tissues that way. And there have been a number of clinical trials of mesenchymal stem cells, which are taken out of your bone marrow in your thigh for the treatment of multiple sclerosis. That's one. For the treatment of macular degeneration, stem cell injections have been tried. And the Jeff Raisman experiment is essentially a stem cell. Is that fair? No, it's not really a stem cell experiment. I think that where we're getting with tissue engineering and 3D printing of, as it were, ordinary cells, may almost make stem cell technology a bit of a blind alley. That's my view, but it's not a very informed view. I mean, I think it's very important research and could continue, because you generally find what you're not looking for, as Alexander Fleming remarked. But stem cell therapies, well, again, it's what I was saying in respect of fad diets. There's a lot of quackery around and desperate patients, going off to far-flung parts of the Far East for injections with God knows what that are called stem cells. So, I don't know. What do you think?
Well, I only read what I see, of course, but I really see what I read. But I was thinking it would go down the line, really, of engineering a person that you want to be.
Yes.
When you're saying it is more of an injection of a remedial part of the body or whatever's going on with
Yes.
but I saw it more as being able to build the ideal person going forward, whatever that ideal person you want it to be. So you say, well, I'm a designer, I want this,
Yes.
and here is this
Yes.
person.
They're growing, whole organs in the lab. I mean, easy organs, tubular organs, like they can now grow new lengths of artery out of your own cells and, use them for repair. Tubes are easy, bladders are easy, any hollow organ is fairly easy, skin is fairly easy. organs like the kidney are much more complex, but they have started. So I've got a feeling that it will be more tissue engineering and regenerative medicine than stem cell injections, but it's just my gut feeling.
On your gut feeling, Dame Mary, I think we can draw the evening to a close. First of all, I want to thank you all for coming tonight. As I said at the beginning, this is the last lecture of the 2014-2015 series, but we will be back in the autumn with some public debates. If you want to come to Brunel before then, we have the Brunel Festival coming up, and I should probably look at my note actually to make sure I've got that right. As many of you will know, this university has been organizing the annual Made in Brunel show for I think 11 years now. But this year we've decided to do something bigger and broader and to give all final year students the opportunity to showcase their achievements in a project. So the Made in Brunel Festival will not just be about science and engineering, it will cut across the disciplines and will be very diverse. It's not just by and for students and staff, it's also for the local community. It'll run from the 19th until the 21st of May. I think that's a Tuesday, a Wednesday, and a Thursday. And as I said, it's a celebration of student achievement. There is a website, I think it's just brunel.ac.uk, Brunel Festival. So if you're interested in coming along, please have a look. There will be more information coming your way via their website. And it promises, I had a look at the program this morning because I need to be aware of how it's going to impact on the local community and make sure that everyone is well informed. It's incredibly exciting. So please come along to one or more activities. Secondly, there is a cash bar, as always, so if you want to carry on the conversation after the lecture, please do so in the atrium. And finally, I hope you can join me in thanking Dame Mary for her wonderful lecture tonight. So thank you so much.